Calculus students, hello. This lecture will be on something known as L'Hopital's rule. L'Hopital was a French mathematician, and this rule is named after him. Now, a limit is at the foundation of the derivative. Remember, a derivative was the limit as h goes to 0 of the difference quotient. But derivatives can also be used to help find certain limits. The following is known as L'Hopital's rule. Now, suppose you have a fraction or quotient of two different functions, and that this fraction approaches either 0 over 0 or plus or minus infinity over infinity. Now, this could be any kind of limit as x approaches a finite number from both sides or from one side, or as x approaches infinity or negative infinity. These two expressions are called quotient indeterminate forms. Quotient because fractions imply division, and indeterminate because these forms are inconclusive. They do not reveal the true value of the limit if there is one. If your fraction of functions approaches one of these two forms, then the value of this limit will be equal to the same limit but of f prime over g prime, provided this new limit exists or is plus or minus infinity. Let's see this put to use. Find each limit two ways, one using algebraic manipulation and two using L'Hopital's rule. Confirm with technology. For example, in this case, well, as x approaches negative 2 from either side, this numerator alone is a continuous function, so changing this x to negative 2 will give us the limit of the numerator. 2 times negative 2 and then add 4 is 0. This denominator is a continuous function by itself, so plug in negative 2 for both of these x's, so we get 4 minus 4 or 0 for the denominator. This is an indeterminate form. We cannot conclude what the value of this limit is from this expression alone. So what we did in the past was some factoring. We factored out a 2 from the numerator and an x from the denominator. Then we canceled out the reason we were getting 0 over 0 and then substituted negative 2 in for the remaining x's. So in this case, we get 2 over negative 2, which simplifies to negative 1 as the value of our limit. Well, now we have a method known as L'Hopital's rule. Because the original function approached 0 over 0, we can instead do the same limit as x goes to negative 2, but differentiate the numerator, giving us 2, and then differentiate the denominator separately, giving us 2x plus 2. The original numerator was f, and this 2 is f prime. The original denominator is the g function, and this denominator is g prime. Now notice we're not using the quotient rule because I'm not differentiating the fraction. I'm simply differentiating the numerator and denominator as if they were separate functions. Once this is done, you can reassess the limit. Substitute negative 2 in for this x, and we get 2 in the numerator and negative 4 plus 2 in the denominator, and in the end this also simplifies to negative 1. Now when L'Hopital's rule gets used, sometimes this equal sign is given a special notation, such as putting an asterisk or star above it, or by putting L'H to stand for L'Hopital's rule got used. In the second limit on this page, as u approaches 4, the numerator approaches square root of 4 minus 2, which will be 0, and the denominator approaches 12 minus 12, which is also 0. So again, a quotient indeterminate. Let's do L'Hopital's rule right away. So this will be equal to, using L'Hopital's rule, the limit as u approaches 4, the derivative of radical u with respect to u will be 1 over 2 radical u, and then minus 2 will go to 0, and then over, the derivative of 3u minus 12 will be 3. And now I can plug in u equals 4, so I get 1/4 divided by 3. This is like 1/4 divided by 3 over 1, and when I invert and multiply, I get 1/12. Now let's do this the way we did it in the past. I'll rewrite the problem, and before, we would multiply the numerator and denominator by the conjugate of the numerator, and then FOIL the conjugates. Rad u times rad u is u. Then we're going to get plus 2 rad u minus 2 rad u, they'll cancel, and then minus 4. I do not FOIL the denominator, instead I continue to factor it. I'll factor that 3 out and leave the rad u plus 2 as a separate factor. This allows me to see the cancellation of these u minus 4s. Once that's done, then a 4 can now go in for the remaining u's, giving us a 1 in the numerator and a 3 times a 2 plus 2, or 3 times 4, which is 1/12 in the end. I'll confirm just this second one with technology. Here's a graph of the function. Let me change my y-scale. It appears the function is continuous at x equals 4, but if you do a trace, we do see a removable discontinuity, and as x approaches 4, the limit is 1/12. So the missing point would have coordinates 4, 1/12, which I could type in and hit label and show it there permanently. Okay, let's go to the next page. This is just more examples where L'Hopital's rule might be useful. We have 4 limits. First case, let z approach 0. The numerator will approach 4 times 0 is 0, and sine of 0 is also 0. So the numerator approaches 0, and the denominator, well, negative 0, 0, e to the 0 is 1, and 1 minus 1 is also 0. So using L'Hopital's rule, we're going to instead do a limit as z approaches 0, and I'll differentiate the numerator. The derivative of sine 4z is cosine 4z, and then times the derivative of 4z, giving me a 4. And the derivative of the denominator, the 1 will go away. We'll have a negative e to the negative z, and then times the derivative of negative z, which is negative 1, changing this coefficient to a positive 1 instead. And now plug in 0. We wind up with cosine of 0, which is 1 times 4, and plug in 0 into the denominator, we'll get e to the 0, which is 1. And so this limit is 4. Looking at this with technology, I graph the function. The function appears to be continuous, but if you do a trace, you will notice that we have a removable discontinuity here when the input is 0. And the height of that missing point would be 4. Next limit on this page, as x approaches negative 1, the numerator approaches 0 cubed, which is 0, and the denominator. Negative 1 to the 6th is positive 1, and then add 5 is positive 6, and then this will become minus 6. So we do get a 0 in the denominator. So this is a trigger for L'Hopital's rule. We'll do a limit instead. As x approaches negative 1, differentiate the numerator, use the generalized power rule, times the derivative of the inside, which is just 1, so I won't write that, over, and the derivative of the denominator will be 6x to the 5th plus 6. When I try to plug in negative 1 now, the numerator will still approach 0, as will the denominator. This means you can continue to use L'Hopital's rule, as long as you keep getting quotient indeterminate forms. Do another derivative, we get 6 times x plus 1 to the first, chain rule times a 1, and the denominator, 30, x to the 4th. This time, when I plug in negative 1, I'll get a 0 in the numerator and a 30 in the denominator. Well, this is not an indeterminate. This is 0 divided by non-zero, which is just 0. Here's a graph of our function. It does appear to be continuous at negative 1, but if you do a trace, you do see that, in fact, there is a removable discontinuity at the location negative 1, 0. Next limit on this page, if you plug in y equals 1, the natural log of 1 is 0. If you plug in 1 into the denominator, we get 2. Well, this is not a quotient indeterminate. This will be the result of our limit without needing to use L'Hopital's rule. We get 0 divided by 2, which is 0. And the fourth one on this page, as w approaches 0, we get arctangent of 0. Recall the arctangent of x graph. It does pass through the origin. The arctangent of 0 is 0 because 0 is the angle at which the tangent is 0. As w approaches 0, arctangent of w approaches 0. And then the denominator will approach sine of 0, which is 0. So this is a trigger for L'Hopital's rule. So we'll do instead a limit as w approaches 0 and differentiate the numerator with respect to w. We get 1 over 1 plus w squared. And differentiate the denominator, we will get cosine of 3w and then chain rule times 3. And now plug in 0 for the w's. Our numerator becomes 1 over 1 plus 0. Cosine of 0 is 1, so we have division by 3, and we get 1/3 as our limit. I will only graph some of these functions to confirm the work we are doing, but I encourage you to pause the lecture video and graph all of them to make sense of the answers we are getting. Let's go to the next page. Recall the 4 classes of continuous functions below in order of growth potential as x increases toward infinity. K stands for any constant. And then we have a logarithm function where the base is more than 1. That ensures that we have a growing logarithm function. And what this symbol means is that a growing logarithm will eventually exceed any constant. For example, in technology, suppose I have a constant 10 and then a log base e or natural log of x. Currently, the constant exceeds the logarithm. But if you go far enough out to the right, in fact, around 22,000 units to the right, we see that the logarithm eventually overtook and became greater than the constant. The word I like to use for this symbol, I like to phrase it this way, that logs dominate or overtake constants. Now, any power of x, as long as that power is positive, will overtake eventually or dominate any growing logarithm. And any growing exponential, as long as the base is more than 1, will eventually overtake and dominate any power of x. We discussed these 4 classes of functions earlier in the course. During that earlier discussion, we discussed that if you take a function from any class, such as x squared, which is a power of x class, and divide it by a logarithm, which is from a lower class, that the dominant function will overtake the dominated function in such a way that this numerator will grow to infinity faster than the denominator, and this fraction will approach infinity as x approaches infinity. Well, we can use L'Hopital's rule to confirm this. As x approaches infinity, so does x squared. As x approaches infinity, so does natural log of x. Although natural log of x approaches infinity very slowly. But this infinity over infinity is a quotient indeterminate, and it's a trigger for L'Hopital's rule. So instead, we'll do the exact same limit, and I'll differentiate the numerator, which is 2x, and I'll differentiate the denominator, which is 1 over x. Now, before we consider this limit, I recommend that you algebraically simplify this first. So 2x divided by 1 over x, you invert and multiply, and we just get 2x squared. And here, we can clearly see infinity squared is infinite, and then double that is infinite. Here's a graph of our function. and we're doing a limit as x goes to infinity, we can see as we go out to the right, it appears that as x increases towards infinity, that the outputs of this function will also increase forever without bound, approaching infinity themselves. This middle example, we have a log class with a base greater than 1 divided by x to a power, x to the 1/2 specifically, so that's in this class. But this time it's the dominating function that's in the denominator. That denominator will grow faster toward infinity than the numerator will, in such a way that the overall fractions themselves will shrink to 0. But now let's see how L'Hopital's rule helps us. This is a growing logarithm that approaches infinity, and square root of x, any positive power of x, will approach infinity, as x does. The derivative of log base 2 of x is 1 over x times the natural log of 2, divided by, and the derivative of radical x is 1 over 2 radical x. I'm going to invert and multiply, and we get 2 radical x over x natural log 2. Simplify even more. This radical x can simplify with this x, leaving a radical x in the denominator. So you have 2 over radical x times natural log of 2. This limit is 2 over square root of infinity is infinity times natural log of 2 is still infinity. And a finite number divided by a denominator that's growing towards infinity is effectively 0. Here's our function. The claim is that as x goes to infinity, the limit will be 0, suggesting a horizontal asymptote. If I change my horizontal scale, you can see better that the function is in fact heading towards the x-axis as an asymptote. Third example, we have an exponential function with a base more than 1, so that's this class, divided by a power of x, this class. So the dominating function is in the numerator, suggesting that this limit will be infinity. Let's use L'Hopital's rule to confirm this. 1.2 raised to the x will approach infinity as x does, and square root of x will approach infinity as x does. So we use L'Hopital's rule. The derivative of 1.2 to the x is itself times the natural log of that base, and the derivative of square root of x is 1 over 2 square roots of x. I'm going to invert and multiply, and we get 2 square root of x times 1.2 to the x times natural log of 1.2. No more denominator at all. Well, natural log of 1.2 is a positive number. The natural log of something less than 1 would be a negative number. And both of these functions here will themselves approach infinity. So we have a limit that's infinity times 2 times some other positive number. This will be an infinite limit. Fourth example, we have x squared, example of a power function. And then we have e to the negative x. This is a decaying exponential. So instead, I'm going to rewrite this function and do the limit as x goes to infinity of x squared, and then e to the negative x pushes that e to the x to the denominator, and now it's e to the positive x. E is a base more than 1. So now I clearly have in the numerator a power of x, and in the denominator a growing exponential. Well, the dominant function here is now in the denominator, so I suspect that this limit will be 0. Let's use L'Hopital's rule to confirm. The numerator approaches infinity, and so does the denominator. So we do instead a limit. The derivative of the numerator is 2x. The derivative of the denominator is just itself. This still approaches infinity over infinity. So we do L'Hopital's rule again, and the derivative of 2x is 2, and the derivative of e to the x is itself still. This now approaches a finite number 2 over an infinity. This is not an indeterminate. In fact, it's 2 over infinity, which is effectively 0. Fifth example, we have a growing logarithm that's in this class being divided by a growing exponential from this class. So again, the dominant function's in the denominator, so I expect this limit to be 0. Let's confirm. As x goes to infinity, natural log of x goes to infinity, and so does 3 raised to the x. So using L'Hopital's rule, we differentiate the numerator and get 1 over x, and differentiate the denominator, getting 3 to the x times natural log of 3. If I think of that denominator as being over 1 and I invert and multiply, I'm going to get a 1 over x, 3 to the x, natural log 3. And this limit is 1 over infinity, and a constant over infinity is effectively 0. And the last example on this page, we have in the numerator a growing exponential, but just barely because the base is barely more than 1. And this is being divided by log of x. Log of x has a base of 10. 10 is more than 1, so we have a growing logarithm. But the dominant function is in the numerator this time. So I expect the overall limit here to be infinity. We'll use L'Hopital's rule to confirm this. 1.01 to the x does approach infinity, and log x does approach infinity as x does. This quotient indeterminate triggers L'Hopital's rule. The derivative of the numerator is 1.01 to the x times the natural log of 1.01. Keep in mind that this is a positive number. And the derivative of the denominator is 1 over x times the natural log of the base of that logarithm. And this log does have a base 10. We'll invert and multiply. We get x times 1.01 to the x times the natural log of 10 times the natural log of 1.01. Well, both of these terms will approach infinity, so overall, this limit will be positive infinity, confirming our suspicion. Let's go to the next page. On this page, we see 4 limits. Again, x is approaching either infinity or negative infinity. All 4 of these we had done in the past using algebraic manipulation. They can also be done using L'Hopital's rule. Let's look at the first one. This is a rational function. Early in the course, we practiced a method where we identified the degree of the denominator, which is 2, and then multiplied this rational function by 1 over x to that power, both numerator and denominator. Then distribute and simplify, we have 7 over x minus 1 over 2 plus 1 over x squared. And then we noticed that these two fractions here, as x goes to infinity, will approach 0. So the overall limit here was negative 1 over 2. Well, now we can use L'Hopital's rule, and we rewrite the limit. As x goes to infinity, we focus on the leading term. If you focus only on the leading term, it reveals the limit as x goes to infinity. Infinity squared is infinity times that negative 1, and we'll have a numerator that approaches negative infinity. In the denominator, our leading term is this 2x squared. As x goes to infinity, 2x squared goes to infinity, and we get over a positive infinity. Well, any form of plus or minus infinity over plus or minus infinity is still a quotient indeterminate that is a trigger for L'Hopital's rule. We're going to differentiate the numerator, 7 minus 2x, and differentiate the denominator, 4x, and reassess. Well, this still approaches negative infinity over infinity. So we use L'Hopital's rule one more time. The derivative of 7 minus 2x is negative 2, and the derivative of 4x is 4. Now we have a constant, confirming that we get negative 1/2 as our limit. Here's a graph of this function. We just discovered that the limit is negative 1/2 as x goes to infinity, suggesting the presence of an asymptote going off to the right. And I can see that asymptote better if I change my scale slightly. And we can see indeed that the function is approaching negative 1/2. Okay, next example, algebraic manipulation. The highest power term in the denominator is z to the 1. So I'm going to multiply top and bottom by 1 over z. Also notice that z is approaching negative infinity this time, not positive infinity. But our numerator becomes 7 minus z over 2 plus 1 over z. As z approaches negative infinity, this fraction here will approach 0, but this numerator will approach positive infinity because z is going to negative infinity. So this gives me a limit of positive infinity over 2, and infinity divided by 2 is not an indeterminate, it is conclusive infinity. I'll rewrite the limit and see if L'Hopital's rule can be helpful here. Focus on the leading term. As z approaches negative infinity, you would square that to become positive infinity, and then that negative coefficient in the front would suggest a negative infinite limit for just the numerator. And the denominator, this will approach negative infinity, and then plus 1 is still negative infinity. But any form of plus or minus infinity over infinity is a trigger for L'Hopital's rule. So I'll do the same limit, differentiate the numerator, 7 minus 2z, differentiate the denominator, just 2, and reassess. This numerator will approach infinity over 2, and so we get a positive infinity limit here. Here's a graph of our function, and as we go left forever, the outputs do approach positive infinity. All right, third example, using algebraic methods. Notice again we're going to negative infinity. The degree of the denominator is this 2, so I'm going to multiply the top and bottom by 1 over y squared. So we get 7 over y in the numerator, and then 2 plus 1 over y squared. Now as y goes to negative infinity, both of these fractions will shrink to 0. And so the value of this limit will be 0 over 2, which is 0. Rewriting, using L'Hopital's rule, the numerator will approach negative infinity as y approaches negative infinity, and the denominator will approach positive infinity because we're squaring y. But this is still a trigger for L'Hopital's rule. The derivative of the numerator is 7, and the derivative of the denominator is 4y. Well, this limit will be 7 over negative infinity, which is a limit of 0. But it also suggests that we're approaching 0 from below, meaning that the fractions are all negative getting closer to 0. Here's a graph of this function, and as we go left forever, you can see that the function is in fact getting closer to the horizontal asymptote y equals 0, but from below. The outputs are negative, but getting closer to 0. And our fourth example, this is not technically a rational function. These 3 power functions will dominate this natural log. Of the 3 power functions, the highest powers, there's a tie, w to the 1. As opposed to w to the 1/2. So your dominant expressions here are these w expressions. If I multiply top and bottom by 1 over w and rewrite, we get a 4 plus natural log of w over w over, now radical w divided by w simplifies to 1 over radical w, and 3w over w is just 3. This expression will approach 0. Because w dominates natural log of w, this will also approach 0. And our final answer ought to be 4/3. Let's rewrite this and use L'Hopital's rule. As w approaches infinity, the numerator approaches infinity, and so does the denominator. So we can say this is equal to the limit, differentiate the numerator with respect to w, we get 4 plus 1 over w, and the denominator, we get 1 over 2 rad w plus 3. And clearly enough, these two expressions, as w approaches infinity, will approach 0. So our final limit will be 4/3. Okay, let's move on to the next page. Now, in addition to quotient indeterminate forms, there are also product, difference, and exponential indeterminate forms. We'll explore all of these, beginning with product indeterminate. If ever you have a limit of a product of functions that's approaching the form infinity times 0, or even negative infinity times 0, then this is an inconclusive result, and we need to analyze further to get the actual limit. So we have two examples of product indeterminates. The first example will be a limit at infinity, and the other example will do a one-sided limit as x approaches a finite number from the right. I see a t to the negative 1 here, so I'm going to rewrite this function as the limit. We have a t times sine of 2 over t. So this t will approach infinity, and this 2 over t will approach 0. So this green expression will approach sine of 0, which is also 0. So overall, we have a limit that's infinity times 0. Now, our strategy is going to be to algebraically rewrite this in such a way that a quotient indeterminate can be produced, and then I can use L'Hopital's rule from there. L'Hopital's rule only applies to quotient indeterminates. Well, in this case, the way we're going to do that is we're simply going to create a complex fraction. I'm going to rewrite this function. I'll keep the sine expression the same, but instead of multiplying by t, I'm going to divide by its reciprocal, because dividing by 1 over t is the same thing as multiplying by t. And as t goes to infinity, the numerator will approach 0, and so will the denominator. And now I have a quotient indeterminate, and I can use L'Hopital's rule. The derivative of sine is cosine. The argument will stay the same, but then the chain rule is I have to multiply by the derivative of the argument. Well, the argument is 2t to the minus 1, and the derivative of that using the power rule will be negative 2t to the negative 2, which I'll put in the front. We get negative 2 over t squared. And then the derivative of 1 over t, this is also just t to the minus 1, and that derivative is negative 1t to the minus 2, or in other words, negative 1 over t squared. Now, when I invert and multiply, this negative and negative will cancel, and this t squares will cancel. So we do a step of simplification, and we wind up just getting 2 cosine of 2 over t. And now we let t go to infinity again. 2 over t will approach 0, and so the value of this limit will be 2 cosine of 0. And the cosine of 0 is 1, so we just get 2. Here's a graph of this function, and sure enough, as x goes to infinity off to the right, the graph is approaching a horizontal asymptote of 2. The next product indeterminate, this time x is approaching 0 from the right, so this x will just approach 0, but then we have to remind ourselves what cotangent does near 0. Here's a graph of the cotangent of 2x by itself, and as x approaches 0 from the right, you can see that we have a vertical asymptote, and the outputs are approaching positive infinity. So this trig function will approach positive infinity. So overall, this does approach a 0 times infinity, which is a product indeterminate. We need to find some way to express this as a quotient indeterminate. With this trig involved, one approach would be to leave the x in the numerator, but move the cotangent to the denominator by using its reciprocal, which is tangent of 2x. Tangent is continuous when its argument is 0. So this fraction, the numerator approaches 0, and the denominator approaches 0, as x does. And now we have a trigger for L'Hopital's rule. So we'll do the same limit. Derivative of the numerator is just x, and the derivative of the denominator, derivative of tangent is secant squared of the same argument, and then chain rule times the derivative of 2x, which is 2. Secant is also continuous at x equals 0. So we can just plug in 0 at this point. 2 times 0 is 0. The secant of 0 is 1. 1 squared is 1, and 1 times 2 is 2. So we get a limit of 1/2. Here's a graph of our function. We're letting x approach 0 from the right. If we use the trace, you'll notice that we do have a discontinuity here when x is 0. The location of this missing point is 0, 1/2. Okay, next on this page, we have two examples of something known as a difference indeterminate, which occurs when you have an infinity minus infinity. It is tempting to say that this might be 0, but it depends on which infinity is larger. Again, our goal will be, if we have a difference indeterminate, is to find some way to express it as a quotient indeterminate so that we can use L'Hopital's rule. First case, n is going to infinity. Well, here I have a 2 over n, and that's an exponent on e. That is approaching 0, which means e to the 0 will be approaching 1, which means this whole first term, because this n is approaching infinity, is approaching infinity. But then, of course, this n is also approaching infinity. So overall, we do have an infinity minus infinity situation. So my first step will be algebraic manipulation. I'm going to factor out the n from both of these terms. That leaves e to the 2 over n minus 1. Now, as n goes to infinity, this coefficient approaches infinity. What's inside the parentheses overall is approaching 0. So we do have a case of approaching infinity times 0. And so we've managed to turn this difference indeterminate into a product indeterminate. And then the product indeterminate, we're going to turn into a quotient indeterminate in a way similar to what we just did a moment ago. I'm going to leave the e to the 2 over n minus 1 alone, but instead of multiplying it by n, I'm going to divide it by its reciprocal. And now, as n goes to infinity, the numerator approaches 0, and so does the denominator. And so we can use L'Hopital's rule. The derivative of e to the 2 over n will be itself times the derivative of 2 over n. Remember, 2 over n is 2n to the minus 1, and the derivative of this will be negative 2n to the minus 2. And the derivative of 1 over n, that's just n to the minus 1, is just negative n to the minus 2. These n to the minus 2's will cancel. These minus signs will cancel, making a positive. And so this simplifies 2 times e to the 2 over n. Now we can reconsider what happens when n goes to infinity. This exponent will approach 0, so this limit will be 2e to the 0, or just 2. Here's a graph of this function and its asymptote. And sure enough, as we go to the right, the function does approach the asymptote. All right, our second difference indeterminate. We're doing a limit as x approaches 1 from the right, and we have a 1 over natural log of x. This will take some careful analysis. Recall the graph of y equals natural log of x. It crosses at 1, 0. So as we approach 1 from the right, the outputs will approach 0, but from above. My notation will be that this approaches positive 0, meaning we're approaching 0 from above, which means that 1 over a shrinking number towards 0, but from above, will approach positive infinity. Now similarly, x minus 1, as x approaches 1 from above, this will also approach 0, but from above, which means that this fraction also will be approaching positive infinity. So overall, we do have positive infinity minus a positive infinity. We have a difference indeterminate. The strategy we'll use here is to get a common denominator. So I'm going to multiply the first fraction by x minus 1 over x minus 1, and I'll multiply the second fraction by natural log of x over natural log of x. This gives me a numerator of x minus 1 minus natural log of x over x minus 1 natural log of x. Now be careful that you're not lazy and you try to cancel these natural logs. We have subtraction in the numerator that prevents us from doing that. But as x goes to 1, the natural log of 1 is 0. So all four of these highlighted expressions approach 0, meaning that overall this does approach 0 over 0, and this is a trigger for L'Hopital's rule. The derivative of the numerator, we get 1 minus 0 minus 1 over x. Now to differentiate the denominator, I have to use the product rule. So we do the derivative of x minus 1, which is 1, times natural log of x, plus the x minus 1 times the derivative of natural log of x, which is 1 over x. Now this is a complex fraction, so we're going to simplify this by making it non-complex by multiplying top and bottom by the LCD of all the subfractions, which is to say multiply the top and bottom by x. Our simplification takes us to a numerator that is just x minus 1, and the denominator will be x natural log of x plus x minus 1. Now as x goes to 1, this approaches 0, this approaches 0, and this still approaches 0. So overall we're still approaching a 0 over 0, which means use L'Hopital's rule again. The derivative of x minus 1 is just 1, and then to differentiate this product, you got to use the product rule. We have the derivative of x is 1 times natural log of x plus x times derivative of natural log of x, and then continuing to differentiate, we have plus a 1 and then minus 0. Let me simplify this. We wind up getting just 2 plus natural log of x in that denominator. The natural log of x will approach 0 as x approaches 1, and so we finally get a limit that is not indeterminate. We get 1/2. Here's our function. This is the limit as x approaches 1. So I zoom in, and if I do a trace, you will see a removable discontinuity here, the location of which is 1, 1/2. All right, next page. Our final kind of indeterminate are exponential indeterminates. When you have functions that are exponential in nature, there's a base and a power, where the base and power have a limit of the form 1 to the infinity, so the base is getting closer to 1 while the exponent's getting closer to infinity. Or if you have the base approaching 0 while the exponent's approaching 0, or if you have the base approaching infinity while the exponent is approaching 0. These are all indeterminate forms and will lead to the need for algebraic simplification. Now, one identity we're going to use is that if you take any expression, I'll say a, that you can rewrite it as e raised to the natural log of a. This was e and natural log are inverse functions of each other. They cancel each other. Also recall that if you have natural log of b raised to the c, that the c can be brought down as a coefficient and say c times natural log of b. These are going to be two properties or identities related to logarithms that will be helpful in our algebraic manipulation of these expressions. We have 3 examples here, basically one for each of these types of indeterminate. First one, this is a limit as x goes to infinity. This part shrinks to 0, so this base approaches 1 minus 0, which is 1, while the exponent itself is going to infinity. So this does have a limit of the form 1 raised to the infinity. There's sort of a tug of war going on here. The exponent is trying to make the result big, while the base, as it gets closer to 1, tries to produce a result of 1, and the result is inconclusive. So we need further analysis. Well, the first thing I'm going to do is rewrite this function. So we'll do a limit as x goes to infinity, and I'm going to use the property where I change this to e raised to the natural log of, and then just rewrite the function. Because we have a natural log now, I can use the property where this power can be brought down as a coefficient instead. So we have e to the x natural log of 1 minus 3 over x. And now let's assess what happens as x goes to infinity. This coefficient goes to infinity, this argument approaches 1, and the natural log of 1 is 0. So this is approaching e raised to the infinity times 0. Notice that the exponent here is a product indeterminate. So I'm going to manipulate the exponent in a way similar to how I manipulated product indeterminates in earlier examples. Because our exponents get quite complicated, I'm going to use a caret symbol and then a bigger set of parentheses to represent the exponent. So I'm going to keep the natural log of 1 minus 3 over x alone, but instead of multiplying it by x, I'm going to divide it by its reciprocal. And now we have a result that is approaching e raised to the, this is approaching 0, 1 minus 0 is 1, and natural log of 1 is 0. Numerator of the exponent is approaching 0, and as x goes to infinity, 1 over x approaches 0 as well. So we're going to use L'Hopital's rule, but only on the exponent. Recall also that when you differentiate natural log of u using chain rule, you get u prime over u. So differentiating this function times the derivative of the argument. We have a 1 minus 3x to the minus 1. The derivative of this will be 3x to the minus 2. So times 3x to the minus 2. And now we do the derivative of 1 over x, which is negative x to the minus 2. The x to the minus 2's are going to cancel each other. This minus and this 3 make a negative 3, which I can just put here in the numerator. So simplifying, e raised to the negative 3 over 1 minus 3 over x. And now this part here will shrink to 0, and so our exponent will approach negative 3. Here's a graph of our function and its limit. As x goes to the right forever, you can see the horizontal asymptote. Okay, middle example. We only want to define this function for positive values of x because x is a base and we don't want negative bases. So we can only approach 0 from the right. But this is a clear case where the base will approach 0 at the same time that the exponent is approaching 0. This is our middle case of a exponential indeterminate. We're going to rewrite this as e raised to the natural log of x to the 4x. Then I'll use the log property where this power can be brought down as a coefficient. So you have e raised to the 4x natural log of x. As x approaches 0, this will approach e to the 0 times natural log of 0. The graph of y equals natural log of x. As the arguments approach 0 from the right, the outputs approach negative infinity. So we have a 0 times infinite product indeterminate in our exponent. I want to rewrite this in a way so that we have a quotient indeterminate instead. I'll switch to my caret notation. I'm going to leave the 4 and the natural log of x alone, but instead of multiplying by x, I'm going to divide by 1 over x. So this is approaching e raised to the numerator approaches negative infinity, and the denominator approaches positive infinity, and we have a quotient indeterminate in our exponent. So I can use L'Hopital's rule only on that exponent. So e raised to the derivative of 4 natural log of x will be 4 over x, and the derivative of 1 over x is negative 1 over x squared. Now, instead of doing a limit now, I can algebraically simplify this. This exponent just becomes negative 4x. And as x goes to 0, then so does negative 4x. So our limit is e to the 0, which is a limit of 1. Okay, in this final case, this is x going to infinity again. This base will approach infinity, and this fraction is an exponent. It's approaching 2 over infinity, which is 0. So overall, we are approaching an infinity raised to the 0, which is an example of our third kind of exponential indeterminate. So proceeding very similarly, we'll use the log identity first, e raised to the natural log of x plus 5 raised to the 2 over natural log of x. I can use the log property now to bring this down as a coefficient of that logarithm. And I can just make this one fraction. And as x goes to infinity, both the numerator and denominator of that exponent will approach infinity. So we can go straight to L'Hopital's rule, differentiate this numerator. We get 2 over x plus 5 times a 1 using the chain rule. So just 2 over x plus 5 over, and differentiate this denominator, we get 1 over x. So let's simplify this exponent by inverting and multiplying, and our exponent simply becomes 2x over x plus 5. As x goes to infinity, the numerator and denominator of the exponent both go to infinity, so you could use L'Hopital's rule again. Derivative of 2x is 2, derivative of x plus 5 is 1, and so we get, in the end, a limit of e squared. Okay, now when trying to identify indeterminates, you have to be cautious because note that the expressions below do not represent indeterminate forms. Then find each limit. If you have any constant, where this k is any real number, divided by infinity, this will approach 0. If you have infinity divided by any constant, this will be plus or minus infinity, depending on the sign of k. If k is a -2, for example, then this will approach negative infinity. If you have any constant times infinity, as long as that constant is not 0, because 0 times infinity is a product indeterminate. Any other finite number times infinity will be plus or minus infinity, again, depending on whether that k is positive or negative. If you have infinity raised to the k, and let's assume that this k is positive, but not 0. If it's 0, infinity to the 0 is an exponential indeterminate. But if k was 2, for example, or 1/2, or any positive number, infinity to a positive constant will just be infinity. Infinity to a negative constant, like infinity to the -1, that means 1 over infinity, which approaches 0. If you have 0 to the infinity, so think of numbers are getting closer to 0 while the exponent is getting closer to infinity. This is a double effect, shrinking the result to 0 even faster. If you have infinity plus infinity, that's a case of infinity. Infinity times infinity is infinite. Infinity raised to the infinity is infinite. When you're new to this, you run the risk of seeing one of these forms and assuming it's an indeterminate and then inappropriately using L'Hopital's rule. Look at these two limits. As x goes to 0, 1 over x approaches infinity, while cosine of x, cosine of 0 is 1. So this limit is infinity to the 1, and that's just infinity. As x goes to negative infinity, this numerator approaches 0, and x plus 1 approaches negative infinity. So this limit is 0 over negative infinity, which shrinks to 0 all the faster. Okay, and one more page. Sometimes L'Hopital's rule is not helpful. Find the limit below by first trying L'Hopital's rule. As x goes to infinity, the inside of this radical will go to infinity, and the square root of infinity is still infinity, and this denominator approaches infinity. So we do have a quotient indeterminate, which triggers L'Hopital's rule. Recall real fast that the derivative of the square root of u will be using the chain rule u prime over, and then 2 radical u. So when I differentiate this numerator, I'm going to get the argument is 4x squared plus 1. The derivative of that is 8x. And then over 2 times the square root of the same radicand. And then all over, and the derivative of just x is 1. So simplify this. This is really just, in the end, 4x over the square root of 4x squared plus 1. As x goes to infinity, then the numerator does, and so does the denominator. So this is a trigger for doing L'Hopital's rule again. The derivative of 4x is 4, and the derivative of that denominator is just this again. We'll think of this 4 as a 4 over 1, and then invert and multiply. So you have 4 over 1 times 2 times the radical over 8x. And in the end, we wind up getting this limit, which is the original limit. So we've gone in a circle. So instead, the only way to get this limit is to use an algebraic manipulation. Let me rewrite it. I'm going to begin by factoring an x squared out of the numerator, but keeping it inside the radical. So that would leave a 4 plus, and then we would have a 1 over x squared. And this is all over an x. Then we can use the property that if you square root a product, you can square root the factors of the product separately. So I can square root the x squared separately from square rooting this expression in parentheses. Square root of x squared is just x, and then we still have the square root on this portion, and then over an x. Now we can get cancellation of these x's, followed by the observation that 1 over x squared as x goes to infinity will approach 0. So the value of this limit in the end will just be the square root of 4, which is 2. All right, this concludes our lesson on using L'Hopital's rule to help us find limits of functions that have indeterminate forms.